So picking up where we left off. Oh, and I also showed you our Harry Potter witchcraft magnetic fields and superconductors videos, yes? Which has nothing to do with this course, except for the fact that it's got magnets and it's, holy smokes, cool. It was quantum flux and quantum locking and quantum trapping, and holy smokes, was that cool? Okay. So this setup, this idea of a railgun, has some applications. One would be, this is seen as a means of launching vehicles from the International Space Station without the need for rocket fuel. If your space station is right here, you don't want to fire a rocket right next to it. That's bad. That's bad. So what would you do? This has been proposed that on the end of the space station, you put some conducting rails, and you use the spaceship itself as your conducting strip. So you would supply a current from your solar cells. You could have a magnetic field from a couple of big solenoids. Which way would the current be flowing? This way. This way. In the spaceship itself, the current would be flowing down the page. Which way is the magnetic field? Colin, what do these X's mean for a magnetic field direction? Into the page. So if you all point your right thumbs down the page, and can you extend your fingers into the page, which way will this ship feel a force? It's going to feel a force to the right, and you would then be able to launch your spaceship without rockets. And in outer space, whatever velocity it had, of course, would just keep going and going. So you would let it take off, it would coast for a while, and once it was a good safe distance away, then it could fire its rockets. This is a nice way to launch spaceships. Also, electric motors. Where a coil spins in a magnetic field when a current runs through it. The coil does experience motion voltage, which is commonly referred to as back EMF. I don't think we're going to get to back EMF this year, even though it's cool. So this is kind of a maybe. Example 12. So recall we said this starts moving because the battery is sending a current that way. The battery is sending a current that way. If you point your right thumbs up the page, which way is the magnetic field? Out of the page. Which way will this rod feel a force? To the right. But as soon as it starts to move, right? You're using your left hand again, by the way. Yeah, we caught that. As soon as it starts to move, not only is this charge moving up the page because of the current, because it's locked in the bar, which is moving to the right, it's also moving to the right. So it's going to be point my thumb to the right, because that's which way the bar itself is moving, that's which way that proton is moving, magnetic field out of the page. We're going to get an opposing current down. So you ready? Here's our thought experiment. It says this: as the strip continues to speed up at a lesser rate, the induced voltage will continue to grow. What happens when the induced voltage is equal to the supply voltage? Well, what you then have is the supply current equals the opposing current. Okay. If you have 5 amps this way, and 5 amps this way, what's your net current? 0. So what you end up with is and since the force on this wire is Bill, what happens to your force if your net current is 0? Meant to be pretty obvious. Okay, that means the force is 0 newtons. So what's the correct answer when the two currents equal each other, A, B, C, or I guess A or B or C? It's going to move at a constant speed because Newton's first is going to kick in. It's going to keep going at a constant speed. Now, in real life, Devin, actually, because friction exists, it would start to slow down a tiny bit. But as soon as it slows down a tiny bit, then the supply current is going to be bigger than the source current, and so it's going to kind of wiggle its way and hit a constant speed. But this is, in fact, this is V max, little v. This is the maximum speed. You want to know the maximum speed when your source current is exactly canceled out by the induced current. Okay? That sounds like something we could calculate. That sounds like we could actually calculate the maximum speed for a railgun. You wanna? Oh, let's. It says find an expression for the maximum speed of this railgun. Okay. Well, let's call this I source, and we'll call this I induced. On a basic level, it's when your source equals the induced. You with me so far? Except I'm going to write current differently. Another way to write current is voltage over resistance. This voltage is going to be the source voltage. And then put your pencils down or just watch for 1 second. This is also going to be voltage over resistance, except this is not going to be voltage, it's going to be the induced voltage. Give me 1 second here. You with me so far? So really, it's going to be when my source voltage exactly equals my induced voltage. Even easier way to think about it. What is the induced voltage? Well, induced voltage on a wire is BLV. So sort of what we're saying is when your BLV equals your source voltage. Now this said find an expression for the maximum speed of this railgun. Let's get the little v by itself. You want the maximum speed? It's going to be voltage divided by magnetic field times the length. That's the maximum speed. If you want to, you can put a little max as a subscript next to the V. So, for each instance below, it says find the induced voltage, the EMF, the net voltage, the current and the direction, and the magnetic force and the direction. There's 2 questions. Hey, let's cleverly divide our page into 2. And in fact, let's kind of do these simultaneously. We'll do each one so we can compare and contrast. The first thing it asks for is the induced voltage, the EMF. The induced voltage is equal to BLV. It's equal to BLV. And I would argue, Rob, the left-hand side is really, really easy because what's your speed or what's your velocity on the left-hand side?
0.
So what's your induced voltage? 0. On the right-hand side, it's going to be 0.35 L 4.1. Have to get that from the diagram. I was staring at it and couldn't see it because it was typed out. V 8. 11.5? Okay. B. The net voltage. Well, you know what? 320 volts. Because nothing much is happening yet. But in B, really what we're doing, if this is moving to the right, and a magnetic field, pointing my thumb to the right, magnetic field into the page, we are starting to induce a current this way. Remember in the circuitry unit when we looked at opposing batteries? This is why I really looked at that. We do have opposing batteries. So I've got a source of 320 volts, and I've got 11.5 volts going in the opposite way. What's my net voltage? Oh, let's stay consistent in color, Mr. Dewick. Let's even write how we would calculate it. It's 320 minus 11.48. I'll go 308.5. I'll carry an extra sig figure too just to walk through the whole thing. Okay? 305, Mr. Dewick. 308, Mr. Dewick. 0.52 volts. Before we move further, what if this went faster? What would happen to this answer? This answer here, your induced voltage. If V gets bigger, what happens to this? Gets bigger. What happens to your net voltage? And you know your maximum speed is when your net voltage equals 0, when the induced voltage equals 320 volts, my source. That's your maximum speed. Okay? What did C want me to find? The current and direction. Okay. Did they tell me the current? No. But I have another expression for current. Current is voltage divided by resistance. I think it's going to be 320 divided by 8.5 ohms. Current is initially 37.6 amps. Is that okay, Jordan? Yep. And you know what? See, the right-hand side, it's going to be the same thing. It's going to be current equals V over R, but which V? The net or the total voltage? It's going to be 308.52 all over 8.5. 308.52 all over 8.5. 36.3 amps. So looking at what I've written so far, as this speeds up, what's going to happen to my current? Bigger, smaller, or stays the same? Smaller. Keep that in mind. What does D want me to find, Jake? There was a part D, wasn't there? Force. Force, F, right, Colin? Oh, on a wire and magnetic force? This is going to be on your test tomorrow, this equation. What's the magnetic force on a wire? Bill. Bill is on your test, definitely. I haven't taught a bill. Someday if I teach a bill, it's going to be confusing. Although I will say, because for years, ever since I've started teaching, I've always used the phrase "my angels," and this year for the first time, I'm actually teaching an angel, which is kind of cool. So all I need is answer, key, and bill, and I'll have the full gamut. Jake, did they tell me the magnetic field in Teslas? I think they did, didn't they? Yeah. What is it? 0.35. Sorry? 0.35. Current I, 37.6. L, 4.1. Now instead of 37.6, I'm going to go 320 divided by 8.5 to get that number back stored in my calculator. And then I can go 0.35 times that times 4.1. Initially, it's going to feel 54.0 newtons of force. Since there's an unbalanced force, what must this rod do? Accelerate. Did it ask for a direction of the force or not? Oh, which way? So this is going to be right-hand rule. The current is going this way, this way, this way. So I point my thumb down the page, magnetic field into the page. To the right. This works well for me, although it's a little awkward if I use the board. Here, let's do it this way. Oh, that's better. To the right, yes? That also is going to be, that concept will definitely be on your test tomorrow. Here, it's going to be 0.35 times, 36.3. You know what? I'm going to get the full value back. I'm going to go 308.52 divided by 8.5. So it's going. I'll write 36.3, but I'll use my answer button. Times 4.1. $52.1? No. Yeah, 52.1. And is the force bigger or smaller once it starts to move? Smaller? Why? Because current's getting smaller. Okay? Just for giggles, let's find, was it just, what is the maximum speed here? Well, really what we're saying, your maximum speed comes from this equation. This equation, not on your test tomorrow. I'm doing this because it's kind of interesting. Your maximum speed, if you get the V by itself, it's this. You know what? Your maximum speed is when your induced voltage equals your source voltage. Because if I'm inducing 300 volt, what's my source, 320? If I'm inducing 320 volts and my source is 320 volts, what's my net voltage? 0. What's my net current? 0. What's my net force? 0. What's my acceleration? 0, because force is ma. What's, constant speed, max speed. So how fast will this go? 320 divided by 0.35 times 4.1. 223 meters per second, not bad. Okay. You guys are probably too young. Yeah, you were born after the first Gulf War. In the first Gulf War, back in the 90s, the rumor was that Iraq was trying to build a railgun. And so the U.S. had stopped some ships that had long metal tubes on them. And it was possible, perhaps because based on U.S. intelligence, we've learned that sometimes their intelligence isn't quite as good as they think. It was possible those pipes were for oil-ish things, because that's a legitimate use. Or it's possible that they were trying to build some kind of a railgun that would launch large projectiles a long distance. Okay. Did I assign any questions from last day? Or did I just pause? Okay. I'm going to give you a couple here, because this is cool. Number one, you know what? Actually, I think I know which ones I assigned my other class. Donc. No yawning. Wakey, wakey. Did I assign? Yeah. You can try number one. Oh, heck, I'm going to add some more anyways. So let's go. Number two. And then here we go. 3. 4. When it talks about constant speed, what we're really saying is, when does your induced voltage equal your source voltage? Now, looking at this here, Mr. Duick. Yeah, I think that's doable. Um, 8. Okay, we'll stop there. Most of this class is going to be also for you to study and prepare, but I got a couple of cool videos to show you too. I think I said 8, didn't I? Yeah. It says find the initial acceleration, find the force, and then divide by the mass.
1, 2, 3, 4, 8.
I think that's what I said.